Okay, dah record. Alright, okay. Okay, Assalamualaikum and a very good evening to our guest lecturer, IR Dr. Muhammad Aizam Talib, my fellow lecturers, Dr. Dalina Johari, Dr. Nik Hakimi Nik Ali, and Dr. Zulkifli Abdul Hamid. I am Dr. Farnadia Abdul Haris, your moderator for this guest lecture for High Voltage Course, EPO 630 from Shah Alam campus and EPO 616 from Pematang Poh Penang campus. So today we are very lucky to have an expert from industry, specifically in this field, to give a lecture and share his valuable experience for this session. So on behalf of School of Electrical Engineering UiTM, I would like to welcome IR Dr. Muhammad Aizam, Head Advanced Dynamic Service, Tenaga Nasional Berhad Lab Sdn Berhad for this session. So for our information, IR Dr. Muhammad Aizam Talib received the bachelor's degree in electrical engineering from the University of Portsmouth, UK in 1997 and the PhD degree in electrical engineering from University Technology Malaysia, Johor Bahru, Malaysia in 2016. Upon graduation in 1997, he worked with ABB Transmission and Distribution Sdn Berhad, Subang Jaya, Selangor, Malaysia as a design engineer. Since 1998, he has been a research engineer with TMB Research Sdn Berhad, Kajang, Malaysia. He is currently the head of Advanced Dynamic Services. His current research interests include transformer condition monitoring, insulation diagnostic, and dielectric measurement. So I do really hope that all the students can take this opportunity to gain as much knowledge as you can in this lecture. So I will pass this session to our guest lecturer, IR Dr. Aizam. Dr. Aizam, the screen is yours now. Thank you.
Okay, thank you, Dr. Farah. Share my screen first. Okay. Okay, Assalamualaikum and good afternoon, everyone, to the lecturers and also to the students. First thing first, I would like to thank UiTM to invite me, and it is a great honor for me to be invited as a guest speaker for this to the sessions. It's quite challenging actually to present in the afternoon sessions, but I try to make this presentation is more in a simplest way and not to be complicated. So okay, as we know that the title of the presentation today is about on the high voltage testing technique, but we are focused on one of the technique under high voltage testing, what we call is partial discharge measurements. So what I will cover today in this topic is about the introduction of the partial discharge, when we need to perform the partial discharge testing in the lab and also at sites. What is the advantage and disadvantage of the online and offline PD testing? Sometimes we need to test the PD by online method, and sometimes we need to test by offline methods. And then what is the effect of partial discharge in our insulation system, especially in our primary equipments? And then how to conduct the PD measurements and how to analyze the PD results. And finally, I will share some of the measurement and case study, especially on the PD testing for the power transformers. Okay, at the end of the sessions, I hope that all the students able to define the theory of the partial discharge measurements, and secondly, you are able to describe what is the available method for the detection of the PD in the lab and also on site, and then finally, at least you are able to interpret the simple of partial discharge measurement results. Okay, what's the matter with partial discharge, or sometimes we call a PD? The design, operation, and maintenance of any electrical equipment are highly depend on the insulation used on that equipment. For example, if you notice, TNB main intake substations, in Malay we call pencawang masuk utama, require a large land to build up, so that we can install all these primary equipment from the transmission line. We install the circuit breaker, current transformer, instrument transformer, because we need a large area, because the insulation we use is air. That's why sometimes we call this substation as a air insulated substation, AIS. But on the other hand, if you notice, at the uh, high density area, population high density area, for example, in Kuala Lumpur, and also in Penang, for example, in Georgetown, we have a small substations. Why? Because the difference is the insulation used to install of these primary equipments. For the AIS, we use air, but for the high density population area, normally the insulation used to build this substation, we use a gas. That's why sometimes we call this substation as a gas insulated substation. Due to the fact that gas has a higher dielectric strength compared to the air, so we can build our substation design in more complex. We can build the equipment in a small size. So during in service, the insulation system of the equipment under the influence of many stresses, thermal, electrical, and environmental, it will be degraded or deteriorated. So the degradation of the insulation system will create a partial discharge faults. So through the testing, or through this measurement of this partial discharge, it will indicate the process of the degradation of the insulation system. So we can take immediate action to prevent the failure of this primary equipment. But once the PD has been occurs, or it has been incepted, it may increase over time. We cannot stop, but we can slow down, but it still increase over the time. And then it will further degraded or deteriorate the overall insulation system. And then eventually the insulation system will fail, and also it will fail the entire of the equipments. So it is important that we test, we monitor, and analyze the presence of the PD, so that we can avoid the failure of the electrical equipments. So introduction of the PD. What is the PD or partial discharge? It is electrical discharge that do not completely breach the electrode. Electrode is mean between a conductor to the conductor, or conductor to the grounds. So if this fault or the discharge is completely breach the electrode, then we call the phenomena as a fully discharged or arcing. So partial discharge mean partial is mean that it is not completely breached. So what is the definition of PD in IEC 60270? The IC define the PD as a localized electrical discharge that only partially breach the insulations between conductors. So when we design the equipment, we have the a distance between the high voltage to the low voltage. high voltage and low voltage to the ground. So partial discharge only only partially bridge the insulation between the conductor, which can or cannot occur to the adjacent of the conductor. Generally, the discharge appear as a pass, as a pass, and it has a duration less than a microsecond. It is very small and is very fast. So the discharge method is small, but as I said, it can further deteriorate the insulation system of the equipment and finally lead to the failure of the entire equipment. So among the factors that can cause the partial discharge, for example, the overheating of the electric boundaries when we have a charge trap in the surface of the insulations, and also the reaction of the chemical, for example, in the transformer, we have oil, the reaction of the oil and steel, and also with the other material, it will create a partial discharge. Therefore, the presence of partial discharge need to be detected in a non-destructive test. So, in general, the PD is a consequence of the local electrical stress in the insulations. So, when we have the insulation, it can cause the partial discharge due to the electrical stress or on the surface of the insulation. The partial discharge also can happen due to the stress of the surface of the insulations. And partial discharge always generate electromagnetic signal. That's why we can detect the partial discharge from the electromagnetic wave, and also the presence of partial discharge will generate sounds, light, heat, and also the chemical reactions. As an example, when we have the power transformer, when the partial discharge or other fault occurs in the power transformer, it will release gases, and these gases will build up over the time, and then it will generate the sound. So with the presence of the sound, is indicate that the source is active. So it means that when we detect a gas, it's indicate that in the power transformer there is a problem. And then when we put this acoustic sensor, so we can detect the sounds, and through the sound, it can indicate when and where the problem occurs. So I will show later how the detection of the gases and also the sound in the power transformer, we are able to detect the presence of fault, and so we can locate where is the fault, and also when the fault is active. Okay, this is a example of the electrical string or the partial discharge that occurs in these solid insulations. Okay, during this time, the insulation can function as what it is designed. But yeah, as we can see, the partial discharge will grow over the time, and then finally it will break the two terminal between the high voltage to the low voltage, or to the high voltage to the ground. So it will cause the puncture of the insulation system. And then from the partial discharge, finally it will turn to the discharge or arcing activities. So when we need to do the partial discharge testing, there are different stages where we require the partial discharge testing. The first one during the development of the test, so that we can simulate the function of the design of the equipment. The second one, we need to do the partial discharge testing during the type test of the equipments or the test object, for example, transformer, cable, switchgear, and also during the factory acceptance test. And then, of course, after the installation of the equipment at site, we can do the partial discharge testing as a commissioning, as a acceptance test, or even after the failure, we can do the partial discharge testing to determine whether there is a possibility that the partial discharge has been occurs in the equipments. So on the development test, normally it is follow the standards. There is a guideline given governed by the IC for transformer, cable, and switchgear. And also normally we done in the controlled environment. So there is no noise. Everything is controlled. And then for the type test and factory acceptance test is normally done in the factory. This is the common measurement for the acceptance test on the medium voltage and high voltage asset, transformer, cable, switchgear. And normally we follow the standard based on IC 60270. And this measurement also normally performed under controlled environment. We perform no, in the shaded room. And for the on-site measurements, as I said that after the delivery of the asset to the site, we want to ensure that uh, the asset is good. We need to do the on-site measurements. And also sometimes when there is a failure of the equipment, we need also to do the measurements. And then the measurement normally done in this disturbed environment. So we need to have the filtering system, more advanced software so that we can eliminate the noise. Then in terms of online and offline partial discharge testing, we can test the partial discharge through online or offline. Online means that we carry out the measurements without interruption of the power supply. It means that we no need to shut down the electrical equipment. For example, we don't need to off the transformer cable. Through the live operation of the equipment, we can do the partial discharge testing. And then no over voltage needed. We don't need any high voltage source to trigger the discharge. It depend on the normal operating voltage of the equipments. And then through this online PD measurement, we can use for the continuous monitoring and trending analysis. So we can now do the trending of the partial discharge activity from its inception until now it's become bigger and bigger. But through this online measurements, we are not able to do induce voltage. Sometimes we can do the destructive test to see whether the equipment able to withstand the induced voltage. And then for the offline PD, for the offline PD, it means that we need to perform the measurement during the asset de-energized, or it means that we need to stop the operation of the equipment and need the disconnection of the asset from the networks. So through this offline PD measurement, it allow us to do more analysis. For example, we can test at the different voltage, we can test at the different frequency. So we have more data to analyze detail on the condition of the assets. And then also it is a no natural stress condition for the assets. It means that we can test at the lower voltage, so we are not stress the assets. So this some of the example of the evidence of present PD at the different assets. So through this corona camera, we can see the partial discharge activity at this disconnector at the overhead line disconnector through this using corona camera. And then we can see if there is a PD, there is a black when there is not when there is a present of PD, it will increase the surface conductivity. And then we can see there is a black dust and ash in the stator windings. And also when we have imperfect distance between the winding heads and the also the presence of contaminations, it also can cause the presence of partial discharge. And then for the power transformer, so when the power transformer operated at the higher temperature, okay, in this picture we can see the presence of the surface discharge. It's a kind of discharge happen at the surface of the insulation on the cast resin transformer due to the overstress of the operations of the winding. It has caused the surface discharge. And then also we can see here the second picture, the surface discharge on the pressboard insulation. This more on the oil field power transformer. So through this partial discharge activity, through this partial discharge measurement, we are able to detect the presence of these partial discharge activities. And then for the power cable, through the partial discharge testing, PD testing, we are able to detect the threading process in the cable insulations. So no, from the previous video, we can see that when there is a threading occurs from the conductor, co-conductor, it can cause the string until touch to this ground, and then it will cause the failure of the power cable. And then also the partial discharge can also cause the material erosions, which finally can cause the failure of the cable joint. This example of the joint failure when we open the we cut the cable and open the cable joint, we can see the erosions of the joint material. So this example of the present of partial discharge on the rotating machine, transformer, cable, and also overhead lines. So partial discharge in insulation system. So in this slide, I will share what is the causes of the partial discharge in the liquid, solid, and also in the gas. Normally, the design of the equipment is based on these three material. Either we use liquid insulation, either we use solid insulation, and also we use gas insulation. Sometimes there is a mix or combination of these two material, liquid and solid. For example, in the power transformer, we use oil insulation and paper insulation as a liquid and solid insulations. In the cable, we use only solid insulation, but sometimes we have oil field power cable where we use liquid and solid. For GIS, normally the insulation we use only gas. So this is the possible factor that can cause the partial discharge activity in the solid insulation. when we have sharp edges, it means that the sharp area it cause more stresses, and it will create a partial discharge. Second one, when we have a gas bubble or air bubble, it also can create a partial discharge because the bubble it has a dilated strength less compared to the entire system of the insulation. Yeah? So we have a partial discharge there, and also when we have the bridge between these two uh, conductors in the liquids. And the other possible causes is tangential stress in this boundary surface. For the solid insulations, the factor that cause the partial discharge is a crack. When we have a crack in the solid insulation, also sometimes when this manufacturing process is not good, it will cause the presence of void during manufacturing process, and also delamination at the boundary surface. For example, in the power transformer, the conductor we delaminate, we laminate the conductor with this paper insulation, and delamination of this craft paper at the boundary surface will create a partial discharge. And then for the gases, normally the partial discharge is due to the corona discharge when we have sharp edges, or when we have a particle. Sometimes no, we have a contaminations where there is a presence of particle, and this particle will bounce in the GIS, for example, and then it will create a partial discharge. The others is when we have a corona discharge and surface discharge. Okay, the theory and basic of the PD analysis. Okay, okay. When we have the entire insulation system, okay, the gray one is the entire insulation system. But when we have a white, the white one is a white, the presence of white in the insulation. So it means that we have two different material. We have a different no breakdown voltage. So when we apply a voltage here, UT, the blue one is the apply voltage. When we have apply voltage from one terminal, from terminal A to terminal B at the ground, we have apply voltage UT. And then at the same time, when we apply a voltage, there is a small voltage will beat up in the voids where we call U1, U1, the dot line. So the blue one is the applied voltage. The dot one is the voltage applied through this void. So when we apply the voltage, automatically, no, the discharge pass occurs. Discharge voltage occurs, but this void, we know that it has a lower breakdown voltage compared to the entire of the insulation system. Okay, we can see from this picture that when there is an increase the voltage, the discharge pass is increased. But when it reaches the UZ is the discharge level, or the discharge voltage of the void, and then it will cause the breakdowns. So there is a breakdown here occurs, and then it sees that the voltage is still applied, so the discharge pass or the discharge voltage will increase again. And then when the discharge voltage reach to the UZ, it will break down again. And then at the second half, we can see that the voltage is down, so the discharge voltage is also down. And then at the negative pass, it will see similar phenomena to the positive pulse, and then it will create a discharge. So finally, we have discharge pulse or discharge current at the first entered quadrants. So through this measurement of the partial discharge, we will measure the no the discharge pulse or discharge current occurs at the whites. So this process continue. This process is continue when the water is still applied to the entire insulation. So the next slide is on the PD measurement and analysis. So we know that all the defect in the material will be accompanied by the presence of partial discharge. It means that when we have a fault in the insulation, it will create a partial discharge. So through the measurement of the discharge, technically we are able to detect the defects. Even we can identify what is the type of the defect based on no it specific patterns. Okay, we have a different technique to measure or to detect the partial discharge. We can have optical method. We have a mechanical method. We have a electrical method, and also we have a chemical method, and also heat. So through a different method, we are able to present to detect the presence of partial discharge in the insulations. So for the when we use the optical sensor, we can detect presence of discharge in terms of its light, and also we when we use this mechanical sensor or accelerometer, a piezoelectric sensor, we can measure the sound signal, and then when we use a coupling capacitor, we can use the technique to measure the electrical discharge, and also from the dissolved gas analysis, we can measure the presence of a discharge due to the chemical reactions. So what is the analyzing technique that can be used to analyze the presence of PD in the insulations? The first one, normally we can measure the apparent charges, or normally we call a QIC. We know that it is quite difficult or even impossible to measure the PD pass at the voids. So because the pass when need to travel to the sensor will be distorted, and finally the sensor are not able to measure the pass. So through this no measurement, we are only able to measure the discharge at the voids through indirect method. So what I see recommend is we can use apparent charge, QIC, where it is defined as the discharge if injected within a very short time between the terminal of the test object in a specific test circuit, will give the same reading on the measuring instrument as the PD current pass itself. It means that when we do the set up of the partial discharge, we use a PD calibrator to inject the PD pass. So the measuring signal will measure the PD pass produced by the calibrator, and then measure as a apparent charge. And normally it is expressed in picocoulomb. Okay, here is the setup of the PD. This the conventional, or it is a standard measurement of partial discharge. We have HV injection, and then we have a blocking impedance or HV filter, and then we have a divider here, and then we have a measuring instrument or coupling capacitor, and finally we have a PD detector, and then we have a device under test, which is the test object. What we do in the factory or lab, we inject a pulse for the complete connections, and then this coupling capacitor and the PD detector will measure the discharge. So when we apply the voltage, when we apply the higher voltage, so the small discharge will occurs, and then it will pick up by this coupling capacitor and the PDE detector. So because the discharge is very small, normally we use this multiplier based on the previous injection of the signal from the calibrator. Here is the schematic of the propagation of the PD pass. Here we have the test object, and then, for example, we have a white in the test object, and then we inject a signal, and then this signal combined with this PD pass will travel to these measuring instruments. So when we have a phase resolve PD pattern, phase resolve PD diagram, we are able to measure the calibration pass. And then this the noise floor. Normally we need to eliminate the noise floor through this filtration system, or when we test at this Faraday cage, normally the noise floor is no very small. And then what we do is we integrate the energy inside this pass. So the integration of the PD pass will give the apparent charge unit in picocoulombs. The second one we can analyze in terms of inception voltage. What is the inception voltage? It is the lowest voltage edge with PD first observed when we increase the voltage from a level that no PD are observed. For example, during the testing, we increase the voltage slowly until we see the PD pass, and we record at what level of voltage at the first PD occurs. That is the call inception voltage. And then the other parameter that we can analyze is extension voltage. Extension voltage is applied voltage at which PD cease to occur when the applied voltage is decreased from a higher value at which PD is observed. Okay, so when we increase the voltage, the PD occurs, and then we decrease the voltage until we see there is no PD. It is a extension voltage. At what voltage when we decrease the voltage, there is no PD occurs, is called as a extension voltage. So we analyze the basic parameter that we analyze is a picocoulomb, inception voltage, and also extension voltage. Okay, the other parameter we can analyze the PD using a phase resolve PD pattern, PRPD, where we analyze the presence of PD at the different no phase. And then this the ellipse signal. Actually, ellipse and sinusoidal wave is almost the same. where we open the third and fourth cycle into the horizontal lines. So from this PRPD pattern, we are able to detect a different type of defect, because every defect will provide a different signature. For example, when we have a bad contact, corona, discharge in oil and paper, it will give a different PD pattern. And then this example of the characteristic of PD pattern, no, in the oil impregnated paper. So no, when we have a different fault, we will get a different PD pattern. So by analysis the partial recharge through the PRPD, we are able to detect a different fault in the insulation system. So this the example of the PD measurement. This is the last time when no, our team simulate a PD in the labs. So we create a void in the insulation. We put in the oil, and then we increase the voltage, and finally we are able to detect the void in the insulations. So this the typical pattern of PD signal when we have a void in the insulations. And then this example when we have a corona discharge. Corona discharge is normally occurs at the 90 degree, and the pattern it has a flat patterns. So this corona, and then this is the PD pattern. We when we have bubbling in oil, so it will give no a straight line, vertical a straight line in the PD patterns. So through this first result PD pattern, we are able to distinguish or to differentiate the different fault in the installations. Okay, of course, when we do the PD testing, there is a different of noise will exclude in our measurements. Okay, for the disturbance or noise occurs when the circuit is not energized. What does it mean? The lab, in the lab, we have the no noise coming or disturbance coming from the grounding. So our test setup, we need to have a good grounding, and then sometimes the apply voltage is not clean. So this no unclean source will also generate PD. And then the other is outer noise, the environmental noise. And then when we use unsuitable HV connector during the PD testing, also it can cause the partial discharge. So overall, the disturbance when the circuit is not energized is coming from the switching operation in neighbor circuit. Sometimes we need to do the test during the working of the production lines. So this will disturb the PD measurements, and also the radio transmission also can interrupt the PD testing. Then when we energize, the disturbance is coming from the inappropriate HV source. I said unsuitable HV connector, no PD free connection in HV area, and also on this ungrounding, proper ungrounding of the measuring setup. Okay, here I would like to share a video. This the video is taken, I think, last 2 days or last 3 days, just to demo how the PD testing is carried out in the laboratory. Uh, let uh, let's view the video. Okay, this the measuring instrument. We use Omicron MPD. This is the matching impedance, or sometimes we call a quadrupole. This is our HV source, and then this is blocking impedance or HV filter. This HV filter. And then the white one here is a coupling capacitor, or sometimes people call divider. And then we have a test object. We have 11 kV single core cable. Huh? So we need to have a good proper grounding. So otherwise, no, we have the discharge, partial discharge not caused by the void in the insulation, but due to the no improper grounding. So the other terminal we put to the grounding, and then we put the HV source to the no cable conductor. So our foreman connect the HV source to the cable conductor here. Then we open our HV source. Okay. This is a safety switch. And then we connect to this we call MCU. This is the connection between computer and measuring instrument. Converter from the fiber optic to the RS232. And then we open the measuring software. This the basic measuring software. We have advanced measuring software. Okay, we use the calibrator. Okay, we put at the HV terminal, and then the other connection we put at the ground terminal. Okay, this is our scheduled room. Okay, let's say we inject the PD pass at the 5 picocoulomb. So this is our scheduled room or Faraday cage. And here this is our control room. So we need to remove the safety switch, the safety hooks. And then we ask the system to calibrate 5 picocoulomb, and then we see the system will measure 5 picocoulomb. Okay, this is our blocking impedance or HV filter. And then we remove the calibrator before we actual test the cable. And then we close the door, and then we increase the voltage. Slowly we increase the voltage, and then we measure the PD through the ellipse signal. We can transform also to the phase control PD patterns. So okay, that is the video how this PD testing was conducted in the laboratory for the 11 kV single core cable. So, but for the case study, for this presentation, I will share the PD measurement specifically for the power transformers. So, for the power transformer, the PD measurement normally we use mechanical method, electrical. Either we follow standard or non-conventional method using UHF, HFCT, and also TEV. And then the other method is we call dissolved gas analysis. So the PD measurement through the chemical method for the power transformer, normally the power transformer, the big power transformer is filled with the oil. So we go to the site, take the oil sample from the transformer, and then we bring to our lab. So through the we use GC, gas chromatography. We no we have a gas extractor, so we extract the gas from the oil, and then we pass through this GC, chromatography, and the GC we have two sensor, FID and TCD, and this sensor will pick up this wavelength of these chromatograms, and then through this signal through this peak, it will tell what is the gases dissolved in the oil. Okay, this is the structure of the insulating oil in the power transformer. It is normally hydrocarbon based. We have naphthenic, aromatic, and paraffinics. So when the fault occurs in the power transformer, it will open these hydrocarbon chains, and this hydrocarbon chain will form individual atom, and this individual atom will later combine each other to form other gases. So through these different gases, we are able to differentiate what is the type of the fault. For example, when we have overheating fault, it will produce the ethylene and methane gas, and we have arcing in the power transformer. It will generate acetylene. When we extract hydrogen gas, it means that there is a partial discharge occur in the power transformer. So through this chemical method, dissolved gas analysis, we extract the gas from the oil, and we analyze the gas. From the gas, we are able to differentiate what is the possible type of the fault, and one of the fault that we detect is a partial discharge. Then the other method we can use electrical method. This is the setup of the standard of the PD testing. Not only for the power transformer, but also for the cable, switch gear, GIS, and so on. This is the typical setup for the electrical method in accordance to IC 60270. So Z, we have a blocking impedance. We have a blocking impedance or HV filter, and then we have here CA. CA is a test object, and then CK is a coupling capacitor or divider, and then CD is a coupling device or matching impedance, and then it goes to measuring instruments. Okay, here you have seen the video. Here is a HV source, and then we have a blocking impedance or HV filter. We have a coupling capacitor, and then here we have a matching impedance, or sometimes we call as a quadrupole. So from this matching impedance, it will connected to the measuring instrument in the control rooms. And this is the example of the PD measurement using the coupling capacitor in the factory. Okay, here is the transformer. We inject the voltage through the LV and measure the PD at the HV. So we connect the coupling capacitor to the test object, and then here we have coupling no matching impedance no is the quadrupole, and then each quadrupole will connected through this fiber optic, and then goes to the measuring instrument, and then this the coupling capacitor or divider. Okay, the other method we can use bushing of the transformer itself as coupling capacitor, where we directly tap the signal through the bushing tab. Okay, here is the transformer. This is the bushing. Here there is a test tab here, and then we tap. Through the bushing we have a capacitor where it will act as a coupling capacitor. So we connect our coupling device to the test tab, and then we inject the voltage. As I said that we inject the voltage at the LV, and then we measure at the HV, and then this the process how we inject the PD pass during the calibration process. Okay, here is example of the bushing. If we can relate here, this the bushing, this the overall transformer. Here is the bushing. The base is a overall transformer, and then this is our quadrupole or matching impedance, where we connect directly to the bushing test tab. And then here our matching impedance or quadrupole, and then later connected to the measuring instrument. And then here we do the calibrations before we inject the high voltage at the secondary sites. Okay, according to IC, it's allowed the measurements of the frequency is from 30 kilohertz until 1 megahertz. This is the tolerance of the frequency given according to IC. So when we do the measurements at the factory, and then later, for example, we do the measurement at the on-site because on site we have a noise. What we do normally, we test the PD at the higher frequency. So the PD at the different frequency, it will give a different picocoulomb. So we are not able to compare apple to apple between the measurement at the factory and also at sites. At the factory, the maximum frequency up to 1 megahertz. On site normally no the tester use up to gigahertz to eliminate the noise. Then this is the test sequence of the PD test on the power transformers. We can see this is the apply voltage, and then from this enhancement we see what is the level of the inception voltage, and then we pre-stress, and then we no reduce the apply voltage, and then we measure the extension voltage, and then we sustain the voltage up to 1 hour, and then we measure the PD level for the power transformer. The PD level for 1 hour must be less than 300 picocoulomb. So more than picocoulombs mean that the equipment has failed the PD testing. Okay, as a summary of IC 60270 PD measurement, it is a calibrated measurement. If other subsequent test is test according to IC 60270, we can compare the measurements. We can quantify its apparent charge, so it can be used as acceptance test. For example, I said that for the factory testing on power transformer, the acceptance test is 300 pico coulombs. But for site testing, there is no standard yet to quantify what is the level of PD as a acceptance test. And then through this electrical PD test, we can detect, quantify, and classify what is the type of PD through this phase resolve PD patterns. And then for the electrical method, we can also use HFCT, high frequency CT. This is called non-conventional. IC027O considered as a conventional PD testing. But other than that, we call it as a non-conventional. For example, we use CT, where we put at this ground terminal, or at this conductor, or the neutral conductor. The theory is when there is a PD occurs inside the transformer, it will generate this electromagnetic wave. And then this electromagnetic wave will radiated, and then it will travel to the ground. So when we clamp the HFCT at this ground terminal, we are able to detect the pulse currents. And then transient at voltage. The other method we can use is transient at voltage. This TEV is rely on the concept that when the PD occurs, it will create a current spikes in the conductor, and also to the earth metal surrounding of the conductor. And then uh, when PD occurs, as I said, it will generate electromagnetic wave or energy, and this electromagnetic wave will travel until it reach to this conductor or metal, and then it will induce the current spike. And then when we give a gaps between the internal and external, this current spike will travel through the surface from the inner surface to the outer surface. So through this TEV sensor, we are able to detect the presence of PD in the test objects. So it's more detailed explanation of the TEV. When there is a partial discharge occurs, it will generate this electromagnetic wave or electromagnetic signal. And then when this electromagnetic wave hit to the surface of the conductor or to the metal, it will create a current spikes, and this current spike will travel along the surface of the conductor. And then when we provide a gaps, so this current spike will travel to the outer surface of the equipment, and then when we use the TEV sensor, we are able to pick up this current spikes. So this example of the TEV measurement on the transformer cable box. It only can be applied if the insulation used is air. So when we use gas or liquid, so we are not able to use TEV. We need to use other sensor, for example, SFCT and also UHF sensor. And then this example, the TEV measurement on the switch gear. Okay, the other sensor, electrical method, we can use UHF sensor, where we put a sensor inside the transformer. We put a sensor inside the transformer. So when there is a PD occurs in the transformer, it will generate the electromagnetic wave, and it will be picked up by the UHF sensor. So summary of the non-conventional PD measurement. So we cannot quantify the apparent charge. So it's more on the detection and also the trending purpose. And then through this PRD PD pattern, we are able to classify the fault. Then the advantage is the test can be performed without service interruption. We are no need to shut down the transformer or cable or switch gear. We just put the sensor, and then it will pick up the PD signal. But the challenge is sometimes the PD propagating from the nearby equipment can also will pick up by the measuring instrument. So it is difficult for us to differentiate whether the PD is coming from the actual equipment that we test, or from the other equipment nearby of the test object. So we need more advanced filtering system or more advanced system to eliminate the noise or the signal coming from the other equipments. Okay, the other method we can use PD measurement using acoustic. Using acoustic. So through this acoustic measurement, we use a piezoelectric sensor where we put a sensor around the transformer. So when the PD occurs in the transformer, it will generate the sound. So this sound will be picked up by the acoustic sensor. So through this different sensor, based on time of the arrival of the signal to each sensor, we are able to pinpoint the location of the PD. So mainly the objective of the acoustic PD is to locate the source of the sounds, and then to identify at what condition it will produce this acoustic emission, whether during this high load, temperature high, or during this operation of the tape changer. And then it is more provide more useful information for the operation and maintenance decision, especially when no the asset owner no need to untank or need to open the transformer. So through this PD measurement, we are able to pinpoint the exact location of the faults. So other source of energy, okay, sometimes the challenge is raindrop hitting the tank also will be picked up by the acoustic sensor, and then the overheating of the oil also will be picked up the sensor. Sometimes when oil is circulate in the transformer, it will generate a sound, and this also will be picked up by the sensor. So normally to understand at what level of the activity is active, normally we do the measurement for 24 hours. So we have a complete cycle, the operation of the power transformers. Here we put a sensor. When there is a PD occurs in the transformer, it will generate this acoustic emission wave. And then when we have a different sensor, based on the calculation of arrival time of each signal coming to the sensor, we are able to pinpoint the location of the faults. So this the typical acoustic signature. We analyze in terms of its amplitude, rise time, heat, durations, energy, and so on. So here we put a different sensor. We have a PD based on arrival time of each signal reached to the sensor. We are able to pinpoint the locations. So we can see the guideline on the acoustic emissions for the PD in the power transformer based on IC 57.127. And then example summary of the acoustic PD measurement. It is a non-destructive online applications. Immunity against a wide range of disturbing signal on site. Okay, because the transformer tank itself will act as a shield. So the signal outside from the transformer not disturb the signal, the electromagnetic signal in the transformers. And then through this acoustic measurement, we are able to locate the PD activities. But the signal attenuation depend on the PD set. Sometimes it's quite difficult to pinpoint because if the fault occurs at the inner winding, for example, at the LV winding and core, the signal need to travel from the source to the tank of the transformer. There is a lot of barrier spacer a press board, so the signal become weak, and finally it is not able to reach to the sensor. Sometimes we know there is a fault in the transformer due to the limitation, the signal attenuation. We are unable to locate the faults. Okay, this example of the acoustic PD measurements. So here we put a sensor around the transformer, and then we measure exactly the length of the transformer, X, Y, Z, and then we need to measure exactly what is the location of each sensor. Okay, this is the acoustic sensor put on the transformer tanks. And then finally we are able to pinpoint where is the location of the pod. This from the top view. uh, okay, on the case study, one of the successful case study on the PD measurement on the power transformers. This the 132 kV power transformer during the induced voltage test in the factory. We carry out the also the PD testing by electrical methods, but it failed. So we put acoustic sensor on the transformer. Only one sensor are active. So since the transformer already in the factory, so we open the transformer, and finally we are able to find what is the root cause. We found the internal flashover located at the Y phase of the windings here. Okay, you can see this broken strap due to this arcing, and then shorting of Y phase of limb laminations between the joint of a yoke and limbs. Okay, the other case study, these are small distribution transformers. Okay, we do a test, a complete test on the dissolved gas analysis, and also electrical routine testings. Okay, we got a gas here that said that when there is a presence of high hydrogen, it means that there is a possibility of partial discharge as occur in the power transformer, and also maintain more on the overheating of the transformers. Uh, uh, and then through this dual triangle, the interpretation said there is a tumor fault in the transformers. And then we do electrical diagnostic testing, or the routine testing has passed, but we decide to pinpoint where is the possible locations of the fault, no, the possible location of the high gas generations. So we put a sensor around the transformers. We put a sensor around the transformer here. Uh, and then finally we locate two possible area. Put two possible area. And then we measure again at what location the area. Okay, this the area of ABC here. ABC, and then this the area of Z. Okay, this is the possible area of Z. So we know that this transformer has a problem based on the soft gas analysis. There is a overheating and partial discharge. So through this acoustic emission, the measurement also locate a possible location where is the possible high gas generation. So finally, we decide to untank the transformer. So here, the process of untanking the transformers. Okay, I need to speed up. Okay, so we untank the transformer tank. Here we untank slowly. Okay. So we remove all the oil from the transformer, and then we open the transformer tanks. And then we can see the transformer winding. Here the transformer winding, red phase, yellow phase, and the blue phase. Okay, so we untangle the transformer here. Okay, so the tank is completely removed. And then on the left, the transformer winding and also the tap changer. So we measure again from the acoustic measurement. We measure again where is the possible location of the no faults. That's it. So finally, what we got here? Okay, there is a no determinal connection between the winding and the tap changer. The terminal has been burned. So we can see there is a arcing sign here, overheating sign here. Then the insulation paper has been burned. So this the causes why it generate fault gases in the power transformers. And then the other case study here, it is a step up generator at one of the biggest IPP in Perak. So similar issue, the gas is high. So the asset owner try to find where is the location of the fault, so that they can able to do some rectification to avoid the no failure of the total transformers. So we put a acoustic sensor here, and then we found a few locations from our measurements. Here, when we have internal drawing of the transformer, we can exactly pinpoint where is the location of the faults. Here, so we measure again the possible fault location on the generator step up unit transformers. And finally, when we open the transformer, we can see there is a yeah, okay, so there is a arcing sign. You can see there is a arcing sign, awaiting sign at the change over selector contacts. Here we can see red phase change over selector contact has been burned, and also yellow phase, some sign of overheating. The blue phase is not so bad, but the grid effect is on the red phase change over selector contacts. So we have repaired this problem, and then we put again the operation of the transformer. So it means that through the PD measurements, we are able to detect early the fault in the power transformer. We take immediate action to avoid the failure of the transformers. Yeah, on the last topic, more on the advanced PD analysis. As I said, that the challenge to carry out the PD activity at site is more on the noise or disturbance. So it is quite difficult to separate the PD signal from the noise. So through this advanced PD analysis, we are able to differentiate between the PD and noise. Okay, what is the advanced analysis for the PD detection? Here, IEEE has come up with the measurement of PD. In AC electric machinery. They are suggest on the analysis of the magnitude and polarity of the maximum PD pass. So we plot the pass amplitudes against the voltage phase angle. Here is the phase resolve PD pattern, and then this is the plot of the PD pass against the phase angle. And then from this pattern, we are able to differentiate between the noise and also the actual PD. And then the other advanced analysis, we can use TF map, where we upload the PD pass in terms of its time and frequency, and then okay, this is the time, this is the frequency, and then we have got a different cluster. And then let's say we no select this cluster, and then we retransform again to the phase resolve PD pattern, phase resolve PD pattern. So we are able to differentiate the different PD or even a noise. For example, here when we have a noise, this excited noise, and then this is the external discharge, this the cluster for the external discharge, and then this is the cluster for the micro wide, and then this cluster for the discharge due to the bar to bar or bar to the ground activities. And then the other advanced PD analysis, we can use synchronized three-channel or multispectral analyzer, where we plot the signal, three signal at the different frequency or at the different phase. Okay, we have a phase resolve PD pattern. We plot at the different no frequency or different phase. Then we got a certain cluster, and then we transform again to the phase resolve PD pattern. So we are able through this no three channel or multispectral analyzer, we are able to differentiate between the noise, internal PD, or we have external noise plus crosstalk. Here, okay, here is the example from the standards, and then here example, for example, okay, this the transformer. Let's say the PD occurs at the no blue phase. It means at the blue phase, we will have a higher magnitude compared to the other phases. Because when we put a sensor on the phases, all the signal will be the PD signal will be picked up by the measuring instrument at the other phase, but with the different volume. So it means that the instrument, the PD detection at the blue phase will pick up higher magnitude compared to the yellow and reds. So here when we plot to this no different cluster on the phase 1, phase 2, phase 3. Okay, here how to understand. We know that PD at the blue phase have a 900 picocoulomb. So we plot 900 picocoulomb, and then yellow is 700. Okay, this for phase 2 yellow, this 700. And then for the red phase is 500. So this the 500 of the red phase. So so this the cluster of the PD activities. What happen when we have noise? When we have outside noise or disturbance, all the measuring instrument will pick up with the no almost similar amplitudes. So when we plot into these different three signals, here we have on the phase 1, on the phase 2, and then phase 3 is go to central. So by different cluster at the different positions, we are able to differentiate the PD activity in the transformers. So as a conclusions, the partial discharge can occur in the different type of insulating medium, either it is in the liquid, solid, and gas. So from the presentation, we have seen that we have seen that we are able to detect the PD using a different technique to cater a specific PD activity, either in the liquid, solid, and gas. And then through this early detection from the case study, we have seen that through this PD activity, through the PD measurement, we can early detect the PD activity, so it able to prevent the catastrophic failure of the transformers. And then we can use a different technique for the PD measurements. We have mechanical, we have electrical, we have chemical, and so we have optical method to detect a PD. And then we need no advanced analyzing tool, especially at site, to separate the PD source and noise during the PD measurements. So I think that's all for my presentation. My presentation almost 1.5 hours talking.
Okay, thank you very much, IR Dr. Muhammad Azam. So that was a very informative and comprehensive lecture. So now I would like to open a Q&A session. You can ask the question directly to our speaker. Just click the raise hand, then I will unmute you, or you may drop the question in the chat room. So let me check. Do we have anyone would like to ask the question? Maybe from the students?
Assalamualaikum, Dr. Aizam.
Waalaikumsalam.
Okay, we
Saya
have a
ni
question from our lecturer.
Hakimi. Saya ni Hakimi, Dr. Aizam.
Dengar.
Dengar Maybe I can ask you one question lah. I think this is a very interesting topic and interesting question lah for the student to know. So what is the demand in high voltage area nowadays in industry? So apa keperluan high voltage punya student ni dalam industri kita kat Malaysia sekarang? Adakah demand dia terlalu tinggi ataupun tak ada demand? Ataupun berdasarkan pengalaman ayat Dr. Aizam lah sebagai dalam industri high voltage ni, macam mana demand pekerjaan?
Oh,
Malaysia?
okay. I relate this not actual on this PD lah kot. But it's more on the prospect of high voltage engineer or electrical engineer for the future demand kan. Okay. We can see that every building we need a high voltage. For example, factory, let's say micro electronic factory, they need a high voltage. I know that even macam Intel or ST microelectronic, ST microelectronic, they take 132 kV source from TMB. So and then they maintain itself dia punya substation tu. So in that case, we still need electrical engineer in terms of high voltage, need to do the maintenance, testing, and also do the operations. And then of course TMB still use the electrical engineer. Then even kalau sekarang ni pun when we migrate from the grid to the RE semua, still use the high voltage because the solar farm tu dia akan connected to the grid where we use the 33 132 kV apa ni semua. And then we need to maintain the transformer, circuit breaker apa ni semua tu lah. So macam tu lah I punya that's I can answer lah Dr. Nick.
Boleh. Kadang-kadang ada student, some of the students say, oh, why we need to be a electrical engineer? There's no demand out there. So sebab dia orang tak tahu apa keperluan industri. So that's why saya tanya soalan tu kepada ayah Dr. Aizam.
Dia ni satu. Kalau kita ambil if we take the professional engineer, okay, when we register as a electronic, our professional engineer cannot cover the electrical. They cover only electronic. But when we register as a electronic engineer with board of engineer, it will cover the electronic as well.
Faham, betul.
So kat situlah dia punya kelebihan of as a electrical engineer tu kat situ.
Betul.
Salah satunya lah kan.
Yes. Farah Nadia, saya rasa ada soalan dekat chat.
Itulah. Okay. So,
Terima kasih,
okay,
Dr.
we
Aizam.
have
Yep.
okay, we have few questions from the chat room. Okay, number one, okay, Dr. Aizam, why it is important to measure partial discharge? This is the first question from the chat room.
Why it is important to measure the partial discharge? It is the it's a way ataupun cara how we ensure that the system is designed according to the standard.
All right. Okay, so next question. Okay, Salam, what type of gases that usually used for our insulation in Malaysia? As we know in our learning, the SFC is a quite effective gases but very costly.
Okay, right now in TMB we use SF6, but in the future, because not only expensive SF6, but it is harm to the environment actually. More research is trying to avoid the use of SF6. If you do a research, we can see that people try to use other gases to replace the SF6. But sometimes still use SF6, but they combine with other gases.
Okay, all right. Okay, and then next question. Assalamualaikum Dr. Aizam. As we know, we have 5 PD detection techniques. However, which one is commonly used?
Depend on the situations and location. For example, in the factory, the standard use is electrical method IC 60270. This is the standard method for the factory testing. But for in the factory, we don't use any non-conventional. For example, using the HFCT, UHF, or acoustic. But when the equipment is installed at the sites, we are not able to perform the measurement according to IC 60270 because it requires us to have a high voltage source. So it's quite difficult to bring high voltage source to the sites. So we need to do other method. For example, non-conventional UHF and also TEV or SFCT. But for the location, because TEV, UHF, and HFCT does not able to pinpoint the location of the fault or the PD activity in the test object, so we need to use acoustic. So through the acoustic, we put a different sensor around the test object, and then based on the arrival of each signal to the sensor, we are able to pinpoint. So my answer is depend on the situation, depend on the applications.
Okay, so next, can we use mega test practical use to detect partial discharge, or does it need specialized equipment for PD itself?
Mega is a different test. Mega is insulation resistant. It is not able to detect a PD. It more on detect the dryness or the wetness of the insulation when there is a puncture or arcing shorted between the HV to the LV, then we can use the mega. But PD is a specialized equipment. We require a specialized equipment, and also require expertise to interpret. Uh. Okay, for example, when we use SA0270, it is a yes or no test. Okay, for example, when we test a transformer, the standard said the PD must be less than 300 picocoulomb. If we got more than 300, it means that the PD test is failed. But when we want to analyze what is the possible type of fault apa ni semua, that one perlukan more knowledge and experience.
Okay. Alright. Next. In TMBR or this field, what is the best method or usual method used to mitigate or prevent PD from happen?
We can prevent if we have a good manufacturing process in the factory. Sometimes when we want to build for example, cast resin transformer, die cast during this mold tu, if it is not a proper mold, dia akan introduce void. So bila the mold, bila di resin tu dah keras, so the weight tu akan tinggal lah, akan apa ni, still reside in the insulation. So that's why it will create a PD. It's not immediately fail during in service, but later when with the higher stress, the insulation aging, it will create the discharge or trim. Yes, we can prevent provided we have a good manufacturing process. But once it is occurs, we cannot stop, but we can slow down. For example, we can reduce the operating temperature. So when we reduce the operating temperature, we reduce the stress to the insulation, and it will definitely will reduce the growth of the PD.
Okay. So next one, I think this one is quite similar from the previous one. May I ask what are the mitigation measures for PD? Mitigation measures for PD or mitigation for PD?
Mitigations.
Measures for PD.
Mitigation measures. I think similar answer. We need to have a good manufacturing. For the on-site, we cannot do anything unless we replace the, for example, when the PD occurs at the, windings, we need to replace the windings.
Okay, next one is quite interesting. Salam, doctor. Is it possible for the insulator to not have PD at all?
Um, it's quite difficult to have a PD free actually. That's why at the factory, for example, in the insulator, it require for example, a cable in the factory, the PD must be less than 10 picocoulomb, 10 picocoulomb. But through our experience, when we test the PD, at least we have 1 or 2 picocoulomb, 1 or 2 picocoulomb. But as long as it less than 10 picocoulomb as required by the standard, then we accept.
Alright. Okay, I think next one pun lebih kurang sama lah. From your experience that work in TNB, is it frequently PD occur? I think the previous answer is
PD occurs, yes. For example, in the transformer, we take the ore sample, we send to the lab, and then from the dissolved gas analysis, we are able to to see that there is a presence of overheating, partial discharge, and arcing. This the I think this is a common phenomena or common issue that we face in our electrical equipments.
All right. Okay, and then we have few more questions. Okay, so what are the key factors influencing initiation, propagation, and detection of PD in high voltage insulation system? Three.
Apa dia? Panggil.
Panjang soalan ni.
Panjang soalan ni. Sekejap What are the key factors influencing initiation, propagation, and detection of PD in high voltage insulation system? The factors lah influence initiation of PD. I think.
Soalan lecturer bagi kat student ni.
Ah, ni soalan test ni kan?
Macam
Ni soalan
soalan
rancang
test
ni.
ni.
Soalan exam ni cik.
Key factor that influence the what?
Influence the initiation
Ah.
and detection of PD.
Ataupun mungkin kita boleh minta Encik Iqbal Mahadi kot untuk voice tanya secara face to face dengan Dr. Aizam. Boleh?
Soalan dia
Encik Iqbal. Boleh Iqbal?
boleh unmute kot? Boleh.
Key factor that influence the initiation of PD kan? The
Initiation.
initiation of PD, contoh based on the what is the material we use, either we use apa ni, solid, liquid or gas, and then what is the size of the voids also influence the initiation of PD, and then the propagation tu bergantung kepada insulation lah we use. Kalau kata apa ni from oil dengan air tu dia punya propagation different. So the overall tu propagation tu dia bergantung kepada insulation kita gunakan, we use, and then also if there is a barrier ataupun blocker yang yang menyebabkan the PD tu unable to travel until to the sensor tu. For example macam transformer bila ada PD dekat inner winding dalam dekat LV, sebab kalau kita tengok kita punya design of the winding transformer tu yang luar sekali tu adalah HV, lepas tu dalam tu LV, and then dalam lagi tu adalah dia punya core. Jadi kalau kata PD tu berlaku pada core ataupun pada LV, and then the signal tu nak travel daripada origin of the source tu, PD tu nak sampai ke tank tu makin lama makin lemah, sebab dia akan lalu apa ni paper, press board, spacer, barrier, oil lagi apa ni semua, and then quality of the oil apa tu pun semua mempengaruhi lah dia punya apa ni propagations.
Okay, alright. So, what are the potential consequences of ignoring or neglecting PD in high voltage system?
The worst case, we can have the failure of the equipment lah. Explosion of the transformer, terbakar ke apa semua ni kan.
Okay. So, next one, are there any new and unconventional methods being studied or developed to detect and reduce the impact of PD in electrical system?
Non-conventional
Non-conventional method.
to reduce.
Yes, to reduce the impact of PD. To detect and reduce the impact of PD.
New method. Dia tanya new method
Ni, lebih kepada new method lah ni. Yang
To
mungkin
impact the PD, impact of PD, it will deteriorate the insulation system. New method to reduce the impact, for example, contoh my area is sebetulnya transformer, so that's why banyak example tu pada transformer actually. We can replace the insulation lah. Contoh, instead of we use this normal craft paper for the insulate the winding tu, we can use thermal upgraded paper, so it can withstand more higher temperature, or we can use synthetic paper, di mana synthetic paper tu dia apa tu, it it can prevent the PD from occurs. To some extent lah, to some extent it can prevent the PD. Kalau kita guna synthetic paper. Tapi kalau kata kita nak less cost sikit, kita boleh gunakan thermal upgraded paper, di mana dia boleh operate at the higher temperature banding dengan normal craft paper tu. At a certain temperature tu dia dah overstress, and then it will create bubble, it will bila ada bubble it will create gases and so on tu.
Okay. Okay, next one. How do partial discharge affect the overall lifespan of electrical equipment? How do PD affect the overall lifespan?
Okay,
of
lifespan. Okay, lifespan. Earlier presentation tu, I said that the design, operation and maintenance any electrical equipment tu dia depend pada installation kan. Maksud kalau kata installation tu bagus, dia boleh survive until maybe 30 to 40 years. But because of the PD, it will deteriorate the installation system lah. So when ada PD, dia deteriorate the installation system, and definitely it will shorten the life of the equipment.
Alright, okay, next one. If PD were to happen, for example, in any TNB sites, what are the steps taken to fix this problem? Do the sites need to be shut down in order to fix them?
Yes, definitely. Contoh macam two cases tu, bila kita detect PD, kita kena shut down the transformer, buka and then fix the problem, baru kita on balik.
Okay. Okay, next one. Why we use mechanical and chemical methods to measure PD2?
We use mechanical, okay, mechanical and chemical. Okay.
Mechanical and chemical.
Yeah, chemical. Okay, normally at the factory we use electrical. But I said that different technique it serve a different purpose. Contoh mechanical, chemical. If we do a testing PD on the transformer using electrical, we need to shut down the transformer. We need to bring high voltage source, and then it require time, money, manpower and so on.
Oh.
But through this chemical method, we are able to determine the PD in a faster way without need to shut down the transformer. For example, it takes about, I think, for the DGA, roughly the cost is about 500 ringgit only. We take the oil sample, no need to shut down transformer, and within, I can say within 1 day, we are able to determine whether there is a PD or not in the transformers.
Okay,
Okay.
Dr.
And
Azam,
then
we
for
have
the
3 more questions.
For the mechanical, mechanical is more on the acoustic. It is purposely to locate the source of the fault. We are not able to locate the fault based on the chemical and also based on the electrical. Only through this mechanical, it means through this acoustic method.
Okay. So next one, are there any emerging technologies or novel approach being explored for PD measurement in HV system nowadays? New technology for PD measurements, I think.
PD measurement, I can say that we can use optical sensor that is built-in during the manufacturing process, so that when there is a PD tu, we can do in the real time punya ni lah. Contoh macam temperature. Normally the temperature of the transformer we measure indirectly through PT 100. But with this new optical sensor, fiber optic tu, we can put at every dip of the winding, so that we can know actual temperature at the middle, top, bottom, outer inner winding apa semua. So I believe that this kind of sensor, optical sensor, or can be also used for this apa ni PD testing.
Okay, so the next one, okay, based on your experience, how do you detect any PD activity as a TNB employee?
Pardon?
How do you detect any partial discharge activity?
Oh, we use electrical, we use chemical, and also we use acoustic tu.
Um,
We use all the method tu.
Alright,
Ah.
okay. Okay, so last one. Theoretically, the safety margin should be around 15 to 25% for insulation level BIL. Does it applicable in real life situation?
In a real BIL, basic insulation level, when we design the equipment, normally we put BIL kan, AC withstand berapa, impas berapa, apa ni semua. Actually is cater for this apa ni worst case scenario punya ni. But in the normal operation tu tak sampai pun. For example, kalau transformer tu 33 kV, for example transformer tu 33 kV, the BIL is actually 75 kV. We design the insulation to withstand 75 kV. Tapi in operation, berapa banyak kali, how many times the transformer face a high voltage stress ataupun high voltage fault sampai 75 kV. Jarang lah. Tapi biasanya kita akan design tu at least double of the operating voltage tu.
Okay, so I think that's all the question from. Okay, so ada lagi the latest
Mana
one.
ni?
What is the biggest tragedies that occurred due to PD in HV? The biggest tragedy that occurred due to PD.
Incident kan?
Incident lah, maksudnya incident ke or
Okay. Dia PD ni, okay, when there is a PD, it not necessary tu dia akan menyebabkan fail, kan? Katalah PD, tapi as long as dia tak breach between the conductor to other conductor or from the conductor to the ground, that equipment can operate aja. Yang jadi tragedi ni, bila dia breach, dia tak namakan PD dah. Bila dia breach, dia jadi discharge ataupun knocking lah. Tapi kita tak nak that PD tu, partial discharge tu become a discharge. Partial discharge is not a tragedy. Bila dia discharge, full discharge between two electrode, itu tragedy. Itu adalah a few cases yang apa ni, contoh when the transformer explode, got a fire apa ni semua. Memang ada case yang bila kita buka do the apa ni forensic engineering tu, kita boleh nampak tracking apa semua daripada one terminal to another terminal. Tu boleh nampak lah tu. Tapi that time tu sebetulnya dah terlambat dah.
Alright. Okay, I guess that's all from the chat room. Okay, actually Dr. Azam, I also have a question. Tadi Dr. Azam ada sebut yang pasal SF6 tu kan, dia harmful to the environment kan. How about kalau the person in charge yang nak handle, is it difficult ke untuk handle this SF6?
This FC6 ni dia tak ada apa ni, tak ada bau, tak ada rupa apa ni semua ni kan. Biasanya dia kalau TNB, kita ada special kamera, kalau ada bocor tu kita boleh detect apa semua tu lah.
Okay. So katakan kalau kita nak buat testing kan, contohlah kalau ada contohlah vacuum, lepas tu ada SF6, kita boleh guna ke test vessel yang sama doktor? Ke macam contoh kalau dah guna vacuum tu memang tak boleh guna dah, ataupun SF6 tu dia ada test vessel for testing lah.
Kalau buat testing rasa boleh je. Sebab
Boleh je.
vacuum.
Oh, okey, boleh. Maksudnya tak ada efek pun lah. Kalau kata macam dia tercampur pun tak ada lah.
Tak ada. Vacuum kan dalam vacuum kan. Vacuum clean lah kan.
Alright.
Tapi
Okay.
saya nak share because F6 ni dia apa ni harmful apa ni semua kan. Jadi dia apa tu kita kena apa ni kena handle with care apa semua ni. Di TMB Research kita ada lab SF6 di mana kita boleh turn SF6 tu to the clean air lah. Kita macam accelerator tu. Bila SF6 yang dah tak pakai tu, yang dah lama tu, kita ada facility to burn and then jadikan dia sebagai clean air apa ni semua. And then kita ada facility juga, SF6 ni dia macam DGA.
Okay.
So bila dia kata ada fault, SF6 tu dia akan turn into different gases. So from the different gases ni kita boleh relate apa yang berlaku.
Okay. Okay.
Tapi that one tu is not my special special area tu. Dia ada guys lah yang handle that one tu.
Dia ada macam proper ni juga prosedur jugalah kan?
Ada.
Okay,
But transformer kita tak pakai SF6. Transformer kita sama ada kita pakai oil, biasa normally oil dengan solid dia kan, paper. But new technology ada pakai SF6 untuk transformer, but in Malaysia we still don't have any single transformer yang pakai SF6 lah.
Okay, kalau currently dekat mana yang dah pakai SFC?
Banyak pakai di Jepun dan China.
Okay.
Sebab kos dia terlalu mahal.
Okay. Okay. Alright. Do you have any question? I think that's all for the Q&A session. So thank you very much for the response all those questions and so on. Okay, I think it's very good questions lah, very good response from the students. Okay, so again, on behalf of School of Electrical Engineering UiTM, I would like to thank to our industry speaker, IR Dr. Muhammad Aizam Talib, for spending your time with our students, high voltage lecturers for organizing such meaningful and valuable webinar, and also to all the students for your participation. I hope we can relate and apply those knowledge and advice from our industrial lecturer, especially in your study and maybe in the future when you work in industry, inshallah. So before we end this session, I would like to invite all of you to have a group photo. So to all the students, can you please help to turn on your camera for a group photo? Dr. Daniel akan ambil ke macam tu?
Boleh?
Dana screenshot
Kejap. Attendee ni sekejap
Okay, attendee boleh ke? Kena
Anak saya tak ada kot kat sini.
Oh, anak Dr. Aizam
saya rasa Dr. Aizam tu saya pernah ajar.
Itu time dinner pun boleh sampai kat ceramah ni.
Okey, rasanya tak boleh lah Dr. Farah. Kejap.
Tak boleh
Kalau
macam mana? Attendee tak boleh
tak boleh sebab dia bukan meeting kot rasanya.
Okey.
Tak clue. Kejap. Dr. Zul tahu ke?
Tu saya tahu ke macam mana nak ni.
Saya pun tak tahu ni. Kita boleh tengok list je kan?
Kita boleh tengok list je.
Sure.
Unmute dulu ke? Boleh?
Tak boleh. Unmute dia tak buka video pun ni.
Ini
Kita
macam
tengok setting. Dr. Dadina cuba setting. Participant dia boleh attendee boleh ni tak? Boleh buka video tak?
participant sekejap attendee. Tak boleh lah. View all. Saya tak boleh. Kita boleh unmute saja. Kita boleh unmute saja. Macam kita berlima je ni. So maybe boleh letak attendance ke tepi kot.
Nampaknya tak dapatlah ambil gambar kot.
Tak dapat. Macam kita je.
Kan? Tak bolehlah tulis I was here with Dr. Aizam kan. Jadi mungkin kita ambil gambar panelis sajalah dengan attendance student je lah kot. Ya?
Okay. Okay.
Sekejap Okay. Okay, kejap. 1, 2, 3. Sekejap Okay.
Student tak boleh ambil gambar.
Minta maaf lah ya. Okay.
Aduh.
Okey, tak apa. Nama ada dalam kita ada recorded.
Nama ada.
Nama ada recorded video, ada attendance pun ada. So,
Okay.
gambar tak dapatlah nak ambil.
Alright.
Nanti Dr. Dalina update dalam IG, nanti dia one tap.
Kita contact dia. Itulah, I think that's all lah. Okay, done yang foto tu. Okay, thank you. Terima kasih ya lagi
Terima
sekali
kasih semua.
Dr. Aizam.
Terima kasih Dr.
semua.
Ya, Aizam.
Assalamualaikum.
Okay.
Terima kasih Dr. Aizam.
Terima kasih Dr. Aizam ya.
Sama.
Okay.
Alright.
Okay, thank you everyone.
Thank you.
Terima kasih.
Hmm?
Dr. Aizam dah keluar. Okay.
Okay.
Uh,
Aduh, alah kenapa tak boleh ya tadi? Kan pula.
sebab
Itulah kan. Dia tak boleh ni kan, dia boleh unmute sahaja. Itulah.
rasa kena ada setting kot ni.
Ramai sedih.
Kan terpaksalah buat lagi webinar
Itulah.
Sekejap, okay, stop recording sekejap.
Okay.
Okay, thank you everyone.
Thank you everyone for your participation. Your